Hello everybody, my name is Xingbo. Welcome to the Engineering Science thesis presentation. Today I'm going to be talking to you about physically interactive flying robots. Now I'm an engineering science in the biomedical option with a mechatronics minor, and my supervisor is Professor Angela Schulich from the Dynamic Systems Lab at UTIUS. So when I say the word flying robots, you probably think of something like this, which is a military-grade drone. Or you might think of something like this, UAV, a manned aerial vehicle used for reconnaissance and surveillance purposes. But there's another class of flying robots that's emerging. So like the quadcopter, which is becoming very popular amongst hobbyists and researchers, these are designed for civilian uses. Some of the more exotic examples include the Festo air jelly, designed for demonstrations, and the air swimmer toy, which is designed for use at home by children. The point of departure for this presentation is to look at how people interact with these flying robots. Now, by far the most common way is to use remote control, and the most conventional method is to use a radio controller. Other devices can be used too. For example, any sort of game controllers, anything with an accelerometer or gyroscope, or basically any other device that's capable of sending wireless signals, such as an electronically sensitive armband. Now, researchers have been hard at work looking for other methods of interaction. Some of them include gestures, speech, and one group was even able to allow the users to control a quadcopter using thoughts and brainwaves. Now, these are great and all, but there are a few shortcomings. So number one, the remote control method is unintuitive because the user must be able to identify and understand the flight dynamics of the robot. And in many cases, they're even required to have special training and have a license to be able to control and pilot them. Some of the other methods require specialized equipment, such as camera systems or microphone arrays. These could be very expensive, and the setup is oftentimes very complicated. It's ones that you find in a research lab, not at a home setting. And lastly, all of these methods focus on one-sided control. The user is piloting the robot, the user is operating it. It lacks interactivity and it lacks a sense of collaboration. So in this project, I looked at physical interactions. These are interactions that's based on contact and force application. There are a few advantages to physical interactions. It can be very intuitive, and when done properly, you will not need any special equipment. And for these reasons, it's suitable for the home settings. And because the robot is able to give you physical feedback, physical force feedback, this can enhance your interactivity as well. There are some disadvantages, however. For one, it's more dangerous because you're exposing your limbs to potentially moving parts and increases your risks of injury. Number two is that the range is often shorter than with any other type of interaction. And lastly, of course, the implementation is not straightforward, especially for a flying robot. It's trivial for a ground vehicle, which can have switches, microcontrollers, and adjustable parts, but these options are not open for flying robots. So the goal of this project is, of course, to come up with a way to allow physical interactions to be used for flying robots. And in short, we want to create a robotic user interface that accepts physical interactions, allowing a user to control the robot entirely using physical contact. And this research can help us better understand how people prefer to interact with robots. In this project, I used a quadcopter, the Parrot AR drone. And for it to work, this quadcopter needs to be able to do two things. Number one, it needs to be able to sense when a user has applied a physical force on this robot with the intent of controlling it. Number two, it must be able to react in a very predictable manner such that the entire interaction process is intuitive. So the design of this whole scheme looks like this. When at first, the user makes physical contact with the robot. This contact is measured by onboard sensors, which can be used to calculate an estimated force. And this, together with the current navigational data and flight data, can be fed into a decision-making block, which decides what commands to issue to react to this force. This command is sent to the quadcopter, which executes the motion and gives feedback to the user. So let's go through this one by one. Number one, sensors. What kind of sensor data available? Well, there are lots. The quadcopter is equipped with accelerometers, gyroscopes, magnetometers, sonars, cameras, a whole lot of them. But we only need a few to be able to estimate the force input. In its simplest formulation, Newton's law, F equals ma. And since A, acceleration, is directly measurable from the accelerometer, we can directly measure that. Torque gets a bit tricky. We don't have a way to directly measure angular acceleration, but we can measure the orientations, or roll, pitch, and yaw angles. And from that, we can use finite differences to calculate or estimate the angular acceleration. Now, because these are real-world signals, they have problems associated with noise and DC bias. So we use some signal processing techniques to remove the noise and remove the biases. Once we have this, we must be able to detect when a user has interacted with the robot. And to do this, I used a very simple peak detection above a threshold technique. It works well once you calibrate it, and the signal processing in the previous step made this quite easy. From here on, there are two possible ways to look at this. One is that whenever you have a force input, you get the force vector, which includes the magnitude and direction of the force. And from that, you trigger a response that's adaptive, so that it could be going in any direction, at any speed, with any sort of magnitude. Number two, it's to detect the peak. Sorry, number two, let's do that again, sorry.
Sure.
So,
yeah, just start that one again.
From here on, there are two,
Give a
my bad.
couple seconds to pause. Yeah.
All right, I'll start that again. So the next step is to figure out when a user has interacted with the robot. So to do this, I use a very simple peak detection above a threshold technique. This works quite well once this threshold has been tuned, and the signal processing in the previous steps really help. So from here on, there are two ways of interpreting this force. Number one is to get the force vector whenever an interaction has happened, which includes the magnitude and direction. And from that, we can trigger a response that can react in any direction with any sort of magnitude. And number two is to categorize the type of force, try to deduce what the user has done to have this reading on your sensors. So for example, did the user flip it from the bottom? Did the user push it from the top or from the side, or try to twist it in any way? And based on that, determine a predefined response that could include static behavior such as land or takeoff. So in terms of the types of reactions, these are a couple that I have implemented in this project. So commands like takeoff and land, so commands like turn around or move along a trajectory, or even do a flip in the air. Now, there's no limitation on what you can do with these. The only requirement is, of course, that these be very predictable and very intuitive, easy to understand. The next part is the decision making. And this is to ensure that once the quadcopter has taken off, it is able to receive commands at the right times, it's able to accept inputs at the right time. So it will answer questions like when to accept input, when can certain commands be issued. You wouldn't want to issue a takeoff command when it's already in the air. And for this, I use a very conventional approach of a state-driven agent design using a finite state machine. Now, this next slide shows you the state transition diagram. I don't want to get into too much detail here, but I just wanted to point out that it controls the program flow. So for example, you won't be able to enter the flight animation state unless you were in hover state to begin with. So lastly, it's important to talk about the feedback to the users. And for this quadcopter, we have LEDs installed which can blink whenever a state transition happens. This is very useful and very important from my experiences. But we also have, as we mentioned before, movement and physical force feedback. And this is very important as well. It completes the interaction loop and allows the robot to communicate back with the user. So next, I'd like to show you a few video demonstrations. In the first video, the robot takes off. Once you flip it from the top, it will blink a red light to warn you, and then it will take off. Once it's in the air, you're able to push it along any direction, and it will generate a trajectory which it will try to follow throughout the duration of its flight. And this is dependent on the direction. Now, let's look at another video. In the second video, I make the robot take off the same way, but once it's in the air, it accepts a different type of, it responds in a different way. So now when I push it from the side, instead of moving along a direction, it performs a little dance in the air in the direction that I pushed it. And to show you this, I push it in another direction, and we'll do the dance in a different axis. And to make the robot land, you simply give it a tap from the top. So in conclusion, this method works, as you see from the videos, but it has its own shortcomings and limitations like discussed above. The range isn't quite a problem because I'm always right next to the robot. However, the big shortcoming is that the quadcopter may not be the best platform because of safety. The propellers are moving at a fast rate, and there's a high chance of injury. So you may be looking at implementing this for another platform, another safer platform. So once we have this method of interaction based on physical contact, we can now evaluate the effectiveness of physical interactions in future surveys. Actually, let's do that again. I'm sorry. So in conclusion, this method works, as you can see from the videos, but it has its own shortcomings and limitations. The short range for this interaction to happen is not a problem because I'm always co-located with a robot. However, the safety consideration is the quadcopter has propellers that are moving at a fast rate, and there's a high chance of injury when I put my hand close to it. So now that we have physical contact interactions, we can evaluate its effectiveness in future studies and surveys and compare it to the other types such as gesture or speech, and we can find out which way the users prefer the most. In the future, I hope to do some work to address some of these problems. For one, I would like to design a customized shell to minimize the risks of injury and to increase safety. And number two, I would like to, as mentioned before, evaluate the effectiveness of various interactions and also various reaction patterns. So what users expect when they push the robot, which ones do they like the most. And lastly, now that we have this, we can try to create a combination of different interaction methods. So perhaps contact along with gesture, which could be far more effective than either alone. So that concludes my presentation. Thank you very much.